As we embark on a journey to understand the fascinating phenomenon of galactic cannibalism, it is essential to first ground ourselves in the vastness of the cosmos, an immense backdrop against which galaxies move, grow, collide, and transform. To truly appreciate how galaxies feast on each other, we must first grasp the sheer scale of the universe and our modest place within it. Our home is a blue planet called Earth, nestled within a solar system dominated by our life-giving star, the Sun. This solar system resides in the Milky Way galaxy, a sprawling collection of hundreds of billions of stars, vast interstellar clouds of gas and dust, dark matter, and enigmatic structures like black holes. But even the Milky Way is just one among countless others, scattered across the observable universe like islands in an unfathomably vast cosmic ocean. The mind-boggling scale of the universe challenges even the most vivid imaginations. To put it simply, the distances between objects in space are so vast that they escape our everyday experience. When we look up at the night sky, the twinkling points of light we see are mostly stars within our galaxy, each so distant that their light takes years or thousands of years to reach us. For instance, the closest star system, Alpha Centauri, lies about 4.37 light-years away, meaning light from that star takes over 4 years to travel here. Understanding these distances requires us to adopt units different from kilometers or miles. Astronomers use the light year, the distance light travels in 1 year, as a fundamental measuring stick. Light speeds at roughly 300,000 kilometers per second, so in a single year, it travels about 9.46 trillion kilometers. Even this incomprehensibly large number is just a stepping stone to the vast distances separating galaxies. Let us scale up from stars to galaxies. The Milky Way stretches approximately 100,000 light-years across, containing billions of stars, including our Sun. Our solar system, by comparison, extends only to about 0.001 light-years. When reaching the furthest edges of the Oort cloud, a vast shell of icy debris marking the outer boundary of our Sun's influence. So the Milky Way is a hypergiant compared to our cosmic neighborhood. Yet even our Milky Way is minuscule when compared to the distances between neighboring galaxies. The closest large galaxy to us, the Andromeda galaxy, is about 2.5 million light-years away. This means that light we see from Andromeda today began its journey long before humans even existed, traveling silently across space and time. What's even more astonishing is the scale beyond our local group of galaxies. Galaxy clusters, such as the Virgo cluster, which hosts over 1,000 galaxies, span millions of light-years across, held together by the gravitational pull of visible matter and an enigmatic substance known as dark matter. Larger still are superclusters, vast groupings of clusters, connecting galaxies in filaments that stretch hundreds of millions of light-years. The cosmic web, a term frequently used in cosmology, describes the large-scale structure of the universe, where billions of galaxies are arranged along filaments and nodes, outlining gigantic voids that are relatively empty. The universe on these grand scales resembles a three-dimensional spider's web, weaving a fabric of matter that shapes the destiny of galaxies within it. But what does this vast scape mean for us? It reminds us of the humility of our place in the cosmos. Our planet is but a speck within the solar system. The solar system a speck within the Milky Way itself one of billions in a universe teeming with life and wonder. And yet, through our curiosity and perseverance, humanity has come to understand much about this grand tapestry. We have unraveled the life stories of stars, glimpsed the formation of galaxies, and even peered back in time to when the universe was young. This enormous scale sets the stage for the dynamic interactions between galaxies, collisions, mergers, and the cosmic dances that astronomers refer to as galactic cannibalism. Such events, while seeming violent on a grand scale, occur over millions or billions of years and shape the evolutionary paths of galaxies, including our own. It is these interactions that we will explore in the following sections: how galaxies grow by absorbing their neighbors, how gravity choreographs these cosmic feasts, and the role such processes play in the universe's ever-changing landscape. Before delving into the specific dance of galaxies, it is worth contemplating the mind-expanding vastness surrounding us. When you close your eyes and imagine the night sky, picture not just the glittering stars, but the immense distances, the sweeping galaxies, and the slow, majestic movements unfolding across eons. This is the cosmic stage upon which galactic cannibalism takes place. Grand, beautiful, and incomprehensibly immense. Understanding this scale helps us appreciate that every star you see, every galaxy observed through powerful telescopes, is part of an interwoven cosmic story spanning billions of years and light-years of distance. It prepares us to witness the drama of galaxies interacting, colliding, and ultimately reshaping themselves and the universe. Next, we will turn our gaze to the life cycle of galaxies themselves, how they form, evolve, and eventually meet their fate through these spectacular interactions, setting the cosmic table for the phenomenon of galactic cannibalism to unfold. Having established the immense scale of the universe and our humble place within it, we now turn our attention to the life cycle of galaxies, the grand cosmic beings that shape the universe's structure. Galaxies are far from static islands in space. They are dynamic entities with origins, transformations, and ultimately, destinies that span billions of years. Understanding this life cycle is essential to appreciating how galactic cannibalism fits within the broader narrative of cosmic evolution. Galaxies begin their existence in the aftermath of the Big Bang, approximately 13.8 billion years ago. In the early universe, matter was nearly uniformly distributed. A hot, dense plasma gradually cooling and coalescing under the influence of gravity. Tiny fluctuations in the density of matter seeded the initial formations where gas and dark matter could accumulate, setting the stage for galaxy formation. The first galaxies were likely small, fragile structures known as proto-galaxies, composed primarily of hydrogen and helium gas, with very few heavy elements. Their emergence signaled the universe's transition from a dark, featureless expanse to a cosmos punctuated by luminous islands of stars and gas. Over hundreds of millions of years, these proto-galaxies grew through processes of accretion and merging, absorbing gas from their surroundings and occasionally colliding and combining with other proto-galaxies. As these fledgling galaxies accumulated mass, the gas within them cooled and condensed, leading to the birth of stars. This process, known as star formation, forged the first stellar generations, which in turn enriched the galactic medium with heavier elements through phenomena such as supernova explosions. These elements, including carbon, oxygen, and iron, are the building blocks for more complex structures. Planets, future generations of stars, even life. Galactic growth during this epoch was often violent and chaotic. Gravity governed the dance of countless gas clouds and dark matter clumps, drawing them into denser regions. Mergers, collisions, and combinations of galaxies played a critical role in this growth. Small galaxies merged to produce larger ones, a natural step toward the diverse galactic forms we observe today. Throughout cosmic history, galaxies have displayed a remarkable variety of shapes and sizes. Broadly categorized, the main classes of galaxies are spirals, ellipticals, and irregulars, each telling a story about their past environment and evolutionary pathways. Spiral galaxies, including our own Milky Way, are characterized by flat, rotating disks with spiraling arms, a dense bulge at the center, and a surrounding halo of stars and dark matter. These galaxies often harbor vibrant regions of star formation within their arms, fueled by abundant reservoirs of gas. The graceful spiral pattern arises from density waves, akin to traffic jams in the movement of stars and gas, that trigger bursts of star creation as material compresses. Elliptical galaxies, on the other hand, tend to be more spheroidal or ellipsoidal, with stars distributed more evenly throughout. They generally contain less gas and dust, and consequently exhibit lower rates of star formation compared to spirals. Their stellar populations are older and redder, with many stars having formed in earlier epochs. Ellipticals often form from the mergers of spiral galaxies, where the violent interaction disrupts the ordered disk structure and creates a more randomized stellar distribution. Irregular galaxies break these patterns, presenting chaotic, asymmetrical shapes with often intense star formation. They can be the remnants of gravitational interactions, small galaxies influenced by neighbors, or the offspring of recent cosmic collisions. The growth and transformation of galaxies are propelled by a variety of factors beyond mergers and accretion. Internal processes such as supernova feedback, explosions that expel gas and regulate subsequent star formation, and activity from supermassive black holes at galactic centers influence their evolution. Likewise, environmental effects, including interactions with surrounding galaxies and the intracluster medium, shape their morphology and composition. As galaxies age, their star formation generally declines. Gas reservoirs become depleted or heated, and without fresh cold gas to collapse and trigger new stars, the galactic population gradually reddens and dims. This fading phase contributes to the aging elliptical galaxies and quiescent spirals that populate the nearby universe. However, the life cycle of a galaxy is far from a predictable, gentle progression. The universe's vastness conceals many dramatic events occurring over hundreds of millions of years. One of the most remarkable phenomena shaping galaxies' destinies is their interaction and collision with neighboring galaxies, often described in terms evocative of feast and famine. Over cosmic timescales, galaxies encounter each other through gravitational attraction, sometimes engaging in prolonged dances, tidal distortions, or outright mergers. These interactions can trigger starbursts, reshape galactic structure, and even feed central black holes. In some cases, larger galaxies absorb smaller ones entirely, a process known as galactic cannibalism. The path a galaxy travels depends on not only its intrinsic properties, but also its environment. Galaxies in dense clusters, for instance, are more likely to experience frequent interactions, mergers, and stripping of gas, which profoundly affects their evolution compared to more isolated counterparts. Importantly, the life cycles of galaxies are interconnected. The cosmic web of gravitationally linked matter facilitates the flow of gas and galaxies into clusters, where mergers serve as catalysts of transformation. Each interaction contributes to the universe's grand evolutionary narrative. To summarize, galaxies are born from primordial matter in the early universe, grow through processes of accretion and merging, evolve in morphology and stellar content, and ultimately meet varied fates shaped by internal and external forces. This continuous cycle of change underscores the dynamism of the cosmos and sets the context for the spectacular interplay of galactic cannibalism to be explored further. In the upcoming section, we will delve deeper into what it truly means for galaxies to eat each other, defining galactic cannibalism, its mechanisms and consequences. But always remember that this cosmic cannibalism is a facet of the ongoing life story of galaxies, embedded within this vast universe that continually evolves. As we continue our cosmic journey, having explored the vast scales of the universe and the grand life cycles of galaxies, we now delve into a phenomenon that captures the imagination both scientifically and metaphorically: galactic cannibalism. The very phrase evokes images of colossal cosmic entities feasting upon one another, a titanic struggle played out on scales and timescales that challenge our understanding. But what does it truly mean for galaxies to eat each other? What mechanics underlie this galactic consumption, and how do these processes shape the universe itself? Galactic cannibalism is a vivid term describing a specific kind of interaction in which a larger, more massive galaxy gravitationally captures and gradually absorbs a smaller galaxy. This process is not swift or dramatic like a fleeting cosmic crash. Rather, it is a slow and prolonged sequence of gravitational encounters, tidal distortions, and progressive assimilation that unfolds over hundreds of millions to billions of years. At its core, galactic cannibalism arises from the fundamental force of gravity. Massive galaxies create gravitational wells that can capture and disrupt smaller wandering galaxies. When the smaller galaxy ventures close enough, it can be trapped in orbit around its larger neighbor. As they circle one another in a mighty celestial ballet, tidal forces, gravitational gradients, begin to pull stars, gas, and dark matter away from the smaller galaxy, forming elongated streams and tails. Over time, through repeated close passes and the exchange of momentum, the smaller galaxy loses orbital energy and spirals inward, ultimately merging into the larger galaxy. During this process, its stars mix with the larger galaxy's stellar population, its gas can trigger new star formation, and its dark matter halo merges into the parent halo. The smaller galaxy's identity essentially dissolves, becoming part of the bigger, evolved system. This is the essence of galactic cannibalism, one galaxy's gradual assimilation of another. This process is most common in dense galactic environments such as galaxy groups and clusters, where the proximity of many galaxies increases the likelihood of close encounters. In these cosmic communities, larger elliptical galaxies often grow by devouring smaller companions, evolving into the massive central galaxies observed at the heart of clusters. Yet the term cannibalism can be a bit misleading if taken too literally. There is no eating in the digestive sense. Rather, galactic cannibalism refers to the redistribution and incorporation of material, stars, gas, dust, and dark matter from one galaxy into another, fundamentally altering the structure and evolutionary path of the involved galaxies. Moreover, cannibalism comes in different flavors, distinguished mainly by the mass ratio between the galaxies involved. When a massive galaxy absorbs a much smaller companion, often a dwarf galaxy, this constitutes a minor merger. These are common occurrences and play a significant role in the growth and evolution of large galaxies, like our Milky Way. On the other hand, major mergers involve two galaxies more comparable in size, usually spirals, colliding and merging to form a more massive, often elliptical galaxy. While major mergers are a dramatic and transformative form of interaction, they too fit under the broad umbrella of galactic cannibalism, as one system ultimately dominates and incorporates the other. The effects of these interactions are profound. Galactic cannibalism can trigger bursts of star formation by compressing gas clouds, fuel the central supermassive black holes, resulting in active galactic nuclei, and reshape galactic morphology. The process can completely erase the structural identity of one or both progenitors, laying new foundations for subsequent cosmic epochs. Observationally, evidence for galactic cannibalism emerges in distorted shapes, tidal streams of stars pulled from victims during close encounters, shells and ripples in galactic disks, and the presence of stellar populations with different ages and compositions that betray a more complex formation history. Thanks to advances in telescopes and sky surveys, astronomers have identified numerous examples of galaxies caught in this act. Satellite galaxies slowly torn apart as they orbit larger hosts, intricate stellar streams wrapping around galaxies like ghostly remnants of devoured systems, and massive ellipticals growing steadily by engulfing their neighbors. From ancient cannibalizations preserved in the Milky Way's stellar halo to titanic collisions in distant clusters, galactic cannibalism is a fundamental force driving the evolution and diversity of galaxies across the universe. In this section, therefore, galactic cannibalism emerges not simply as a dramatic cosmic event, but as a natural recurring phenomenon, a mechanism by which galaxies interact, grow, and reshape the very fabric of the cosmos. As we proceed, we will explore how this concept was discovered and studied over time, from early theories to direct observations, and uncover the forces at play behind these monumental galactic feasts. The story of galactic cannibalism is one that intricately links the dynamic lives of galaxies with the grand narrative of cosmic evolution itself. The concept of galactic cannibalism, the majestic process by which galaxies consume their smaller neighbors, did not emerge overnight. Instead, it unfolded gradually, woven through decades of astronomical observations, theoretical breakthroughs, and increasingly sophisticated technologies. In this section, we embark on a voyage through time to uncover the early theories and compelling observational evidence that led to the discovery and acceptance of galactic cannibalism as a fundamental cosmic phenomenon. Long before astronomers had a clear picture of galaxies as separate island universes, they observed curious peculiarities in the night sky. In the 18th and 19th centuries, telescopes revealed fuzzy, cloud-like objects, nebulae, whose true nature was mysterious. Some appeared as spiral-shaped smudges, known today as spiral galaxies, while others presented elliptical or irregular morphologies. At that time, debates raged on about whether these nebulae were part of our Milky Way or independent galaxies far beyond. It wasn't until the early 20th century, with Edwin Hubble's pioneering work, that galaxies were definitively identified as enormous star systems outside our own. Hubble's classification of galaxies into spirals, ellipticals, and irregulars paved the way for deeper understanding of their forms and behaviors. By the mid-20th century, astronomers began noticing strange features in these galaxies: distorted shapes, elongated arms, and unusual streams of stars. Early telescope images revealed tantalizing evidence that some galaxies were not isolated but engaged in interactions. In 1958, astronomer Halton Arp published Atlas of Peculiar Galaxies, a groundbreaking catalog showcasing galaxies with distorted structures that hinted at recent or ongoing interactions. Arp's work spurred renewed interest in galaxy interactions and mergers. At the same time, theoretical astrophysicists were developing models of gravitational interactions between galaxies. In the 1960s and 1970s, pioneering numerical simulations by researchers such as Alar Tumre and Juri Tumre showed how two spiral galaxies passing close to each other could produce tidal tails, long streams of stars ejected by gravitational forces, and eventually merge. Their work was crucial in establishing that galaxy collisions and mergers were not only possible, but likely common. The term galactic cannibalism itself was popularized in the 1970s, when astronomers observing galaxy clusters noted massive central galaxies that appeared to be swallowing up their smaller companions. These cannibal galaxies exhibited features such as diffuse stellar envelopes and multiple nuclei, clear signs of having incorporated other galaxies. Theoretical insights coupled with observational data began painting a picture of galaxy growth dominated by mergers and accretion. One compelling early case was the observation of the giant elliptical galaxy, M87, in the Virgo cluster. It was noticed that M87's smooth, extended stellar halo contained evidence of stars stripped from other galaxies. Similarly, in the local group, the cosmic neighborhood of our Milky Way, star streams discovered through detailed star mapping indicated past interactions with smaller satellite galaxies, suggesting that our own galaxy had experienced minor cannibalism events. Advances in telescope technology and spectroscopy in the 1980s and 1990s pushed the field further. Observations from the Hubble Space Telescope revealed interacting galaxies with stunning clarity, exposing bridges of gas and stars connecting galaxies in collision. Deep sky surveys unveiled numerous examples of tidal tails, shells, and other signatures of mergers. Meanwhile, observations across multiple wavelengths, from radio waves tracing cold gas to X-rays revealing hot gas in clusters, provided a fuller picture of the processes involved. In addition, astronomers began to piece together galactic histories by studying stellar populations. Variations in star ages, metallicities, chemical composition, and motions served as cosmic fingerprints, unveiling past merger events and supporting the notion that galactic cannibalism was a critical driver of galaxy evolution. By the turn of the millennium, galactic cannibalism had transformed from a speculative hypothesis to a cornerstone of modern astronomy. It was clear that such mergers not only explain the assembly of massive galaxies, but also influence star formation rates, central black hole activity, and the distribution of dark matter. Halos. These early discoveries set the stage for today's multifaceted investigations into galaxy interactions, supported by powerful supercomputers, vast sky surveys, and sophisticated instrumentation. Understanding the discovery of galactic cannibalism is therefore key to appreciating how humanity's vision of the universe evolved, from isolated stars to dynamic, interacting galaxies in an ever-changing cosmos. As we transition next to explore the forces driving these cosmic encounters, including gravity and the elusive dark matter, we stand on the shoulders of these early observations and theories that first made sense of the drama unfolding in the depths of space. In the vast cosmic ballet of galaxies, the forces that orchestrate their movements and interactions are both fascinating and profound. As we delve into the forces at play during galactic interactions, it is crucial to understand that gravity holds the principal role. Yet, beneath the familiar pull of gravity lies an even more mysterious and dominant player: dark matter. Together, these forces govern the complex dance of galaxies, making possible the phenomenon of galactic cannibalism and countless other grand cosmic events. Gravity, the attractive force between masses, is the fundamental glue that binds the universe together. On the scale of galaxies and beyond, gravity controls the orbits of stars, the swirling structure of galactic disks, and the motion of entire galaxies themselves. Without gravity, galaxies would not form, nor would they interact in the spectacular ways we observe. When two galaxies approach each other in the cosmic vastness, their mutual gravitational attraction alters their trajectories. Instead of passing by unaffected, their motions become entwined. This interaction initiates a cascade of effects. Tidal forces emerge, stars and gas clouds feel varying pulls across their lengths, and large-scale distortions develop. These tidal forces, resulting from the differential gravitational pull, rip and stretch the galaxies, generating elongated tidal tails and streams of material that arc through space like ghostly bridges. The strength and outcome of these interactions depend on several factors: the masses of the galaxies involved, their relative velocities, trajectories, and the distribution of matter within them. For instance, galaxies rich in gas respond differently to interactions than those dominated by older stars. The gas can collapse under compression, igniting bursts of new star formation triggered by the collision's shocks and turbulence. But gravity's pull alone cannot fully explain the dynamics we observe. Enter dark matter, an enigmatic and invisible form of matter that outweighs the ordinary visible matter in galaxies by roughly 5 to 1. Discovered indirectly through gravitational effects, dark matter neither emits nor absorbs light, making it detectable only by the gravitational influence it exerts on stars, gas, and light itself. Each galaxy is enveloped in a massive and extensive halo of dark matter. These halos dominate the total gravitational potential, dictating how galaxies rotate and interact. In galactic collisions, it is the dark matter halos that first meet and begin their gravitational interplay, shepherding the galaxies together long before their visible stars and gas clouds come into contact. The presence of dark matter affects the speed and manner in which galaxies merge. It facilitates the capture and eventual fusion by providing a deep gravitational potential well that drags galaxies into coalescence. Without dark matter, many galaxies might simply pass by one another without merging, held apart by their relative velocities. Gravity and dark matter also mediate the transfer of angular momentum during mergers, vital for the reshaping of galactic structure. As galaxies spiral inward, their halos and luminous components interact to redistribute energy and momentum, leading to the transformation from orderly spirals into elliptical galaxy remnants or other morphologies. Further complexity arises from dynamical friction, a process whereby a massive object moving through a sea of less massive particles experiences a drag force due to gravitational interactions. When a smaller galaxy orbits a larger one, dynamical friction slows the smaller body, causing it to lose energy and spiral closer to the center, ultimately being assimilated. This mechanism is key to understanding how galaxies are consumed during galactic cannibalism. Other forces, such as hydrodynamic interactions affecting gas clouds, ram pressure stripping, shocks, and turbulence, also play significant roles, especially in galaxies moving through dense cluster environments. But it is gravity, shaped and deepened by invisible dark matter, that remains the grand architect directing the cosmic encounters. Modern astronomical observations, ranging from mapping rotational curves of galaxies to detailed measurements of galaxy cluster dynamics, continually reinforce the central role of dark matter. Likewise, cosmological simulations incorporating dark matter and gravity reproduce with stunning realism the observed structures and behaviors of galaxies, including mergers and cannibalism. Together, gravity and dark matter choreograph the great cosmic feast. They ensure that galaxies do not merely drift in isolation, but interact, surge towards one another, collide, and merge, crafting the universe's large-scale structure and evolutionary pathways. In the following sections, we will explore more specific types of galactic mergers, major and minor, and how these forces manifest differently depending on the galaxies involved. The story of galactic cannibalism can only be fully appreciated by comprehending the invisible forces and cosmic flows that dictate the rhythm of these celestial consumptions. In the grand cosmic narrative of galactic cannibalism, not all mergers are created equal. To fully comprehend how galaxies consume and transform one another, it is vital to distinguish between the two main types of galactic mergers, major and minor. These categories, based predominantly on the relative masses of the interacting galaxies, govern the scale and consequences of the encounter, shaping the eventual structure and destiny of the resulting galaxy. A major merger happens when two galaxies of comparable size and mass collide and merge, typically with a mass ratio between about 1.1 and 1.3. These cosmic encounters are dramatic and transformative events that can fundamentally alter the morphology, kinematics, and star formation activity within the merging pair. Major mergers are often responsible for the formation of massive elliptical galaxies, which are thought to be the remnants of the collision of two sizable, often spiral galaxies. During a major merger, the gravitational forces become immensely destabilizing. The ordered rotation that characterizes spiral galaxies is disturbed. Stars and gas clouds experience intense tidal forces, and vast amounts of material are thrown into highly chaotic orbits. These interactions can trigger violent starbursts, episodes of rapid star formation fueled by gas compressed during the collision. At the same time, the central regions of the merging galaxies can funnel gas toward their supermassive black holes, igniting highly energetic phenomena known as active galactic nuclei. The end product of a major merger is often a galaxy with a noticeably different structure. Frequently, the collision disrupts the well-ordered spiral disks, leading to a more spheroidal, centrally concentrated galaxy with a smooth appearance, an elliptical galaxy. The stars in their new home follow random orbits rather than coherent rotation, and the gas supply is largely depleted, reducing further star formation. Thus, major mergers not only grow galaxies in mass, but also drive morphological evolution and quenching of star formation. Minor mergers, by contrast, occur when a significantly larger galaxy absorbs a smaller companion, with mass ratios typically greater than about 3.1 or 4.1. These events are more common throughout the cosmos and play a crucial role in the gradual mass assembly of galaxies, like our Milky Way. In a minor merger, the larger galaxy acts as the predator, its gravitational well dominating the interaction. The smaller galaxy, often a dwarf or satellite galaxy, is caught in the gravitational field of the larger and gradually stripped of its stars, gas, and dark matter. Unlike major mergers, minor mergers tend not to dramatically upheave the larger galaxy's structure. Instead, the cannibalized stars and gas are assimilated into the larger galaxy's halo or disk, sometimes creating subtle features like stellar streams, shells, or rings. Despite their less violent appearance, minor mergers can have significant effects. The inflow of fresh gas from the smaller galaxy can reignite star formation in the host. The accreted stellar populations contribute to the growth of the galactic halo and can carry unique chemical signatures, providing clues to the galaxy's evolutionary history. In some cases, repeated minor mergers gradually build up a galaxy's mass and complexity, effectively shaping its outer regions over time. Furthermore, minor mergers can perturb the dynamics of the larger galaxy, triggering the formation of bars, spiral density waves, or warps in the disk. They can also feed the central supermassive black hole, albeit less dramatically than major mergers. In this sense, minor mergers act as more subtle but persistent architects of galactic form and activity. The distinction between major and minor mergers is not always sharply defined, and the outcomes depend not only on mass ratios but also on other factors: the galaxy's gas content, their relative velocities and angles of approach, and the properties of their dark matter halos. Some interactions blur the lines, producing complex features and evolutionary consequences. Studies from large-scale galaxy surveys, coupled with detailed simulations, reveal that both major and minor mergers have been instrumental throughout cosmic history. Early in the universe, major mergers were more frequent and violent, contributing to the rapid formation of massive galaxies. In contrast, in the more mature universe, minor mergers dominate, steadily adding mass and complexity to existing galaxies. For the Milky Way, minor mergers have been especially important. The ongoing accretion of smaller satellite galaxies, such as the Sagittarius Dwarf, influences its halo structure and star formation. Yet, the anticipated future collision with the similarly sized Andromeda galaxy will be a grand major merger event, reshaping both galaxies profoundly. Understanding these two types of galactic mergers provides a critical framework for appreciating the diverse pathways through which galaxies grow and transform. Major mergers tell the story of cosmic upheaval and metamorphosis, while minor mergers weave the quieter tapestry of gradual accretion and refinement. Both are essential threads in the fabric of galactic cannibalism. As we proceed, we will look more closely at how these mergers leave behind telltale signs, distorted structures, tidal tails, and stellar streams that provide the forensic evidence astronomers use to reconstruct the dynamic history of galactic interactions. Together, these clues allow us to decipher the chronicles written in the stars, revealing how galaxies grow by feasting on each other across the spans of time and space. As galaxies engage in their cosmic dances, the intimate and sometimes violent interactions leave behind a wealth of visual and structural clues, silent testimonies to the encounters they have experienced. In this section, we unravel the telltale signs of galactic cannibalism, focusing on the captivating phenomena of distorted structures, tidal tails, and stellar streams. These intricate features not only dazzle our telescopes, but also provide astronomers with forensic evidence, allowing the reconstruction of galaxies' tumultuous pasts. When two galaxies begin their gravitational duet, profound changes ripple through their structures. The immense tidal forces generated during close encounters stretch and twist stellar and gaseous components, radically reshaping appearances. Galaxies that once displayed tidy spiral arms or smooth elliptical profiles become distorted, their shapes warped beyond recognition. These disruptions are the preliminary marks imprinted by gravitational forces, signaling an ongoing or recent interaction. One of the most arresting phenomena arising from these encounters are tidal tails, vast, streamer-like extensions of stars and gas pulled from the outskirts of galaxies. These tails can stretch tens or even hundreds of thousands of light years, curving gracefully into the darkness of space, much like the trails left by comets across a night sky. The origin of tidal tails lies in the gravitational gradients experienced during close passes. The side of a galaxy facing its companion feels a stronger pull than the far side, causing material to be flung outward. Tidal tails are not mere aesthetic curiosities. They are potent indicators of past galactic dramas. Their shape, length, and composition reveal the nature of the interaction, including the masses involved, encounter trajectories, and the timing of the event. For example, galaxy pairs such as the antennae galaxies exhibit spectacular tidal tails that testify to their ongoing merger. These features are often sites of intense star formation, as the tidal forces compress gas clouds and ignite stellar nurseries along the tails themselves. Stellar streams, though more delicate and faint, are another critical signature of galactic cannibalism. These streams are elongated ribbons of stars stripped from smaller satellite galaxies as they orbit and gradually disintegrate within the gravitational well of a larger host galaxy. Unlike the often symmetrical tidal tails produced during major mergers, stellar streams can form complex, looping patterns tracing the decayed orbits of cannibalized galaxies. Our own Milky Way is home to several known stellar streams, discovered through deep sky surveys and precise stellar measurements. Streams like the Sagittarius stream wrap around the galaxy in vast arcs, bearing witness to the ongoing accretion of dwarf galaxies. These stellar filaments are precious cosmic time capsules, preserving chemical compositions, ages, and motions of stars from their parent bodies. Studying them allows astronomers to decode the Milky Way's cannibalistic history and the assembly of its halo. Beyond tidal tails and streams, other structural distortions betray galactic encounters. Shells, concentric, ripple-like structures often seen around elliptical galaxies, are thought to arise from minor mergers where a smaller galaxy's stars are dispersed in arcs. Additionally, warped disks and asymmetrical spiral arms can result from gravitational harassment, where passing galaxies tug on the disks and perturb stellar orbits. Modern observations, empowered by advanced telescopes and wide-field surveys, have uncovered an astonishing variety of these features in galaxies across the universe. High-resolution imaging from the Hubble Space Telescope, alongside data from ground-based observatories, reveal delicate tidal features around galaxies previously thought to be isolated. Each of these details enriches the cosmic story of galactic interactions and growth. Computer simulations complement observations by modeling how gravitational forces sculpt galaxies during encounters. They reproduce tidal tails, streams, shells, and other disturbances, validating theories and providing insights into the timing and mechanisms of galactic cannibalism. By comparing simulated outcomes with actual observations, astronomers piece together the histories of individual galaxies and predict future interactions. In sum, distorted structures, tidal tails, and stellar streams serve as the galaxy's autobiography, etched in stars and gas, chronicling epochs of cosmic evolution. These whispers from past collisions guide us toward deeper understanding of how galaxies assemble, evolve, and sometimes devour their companions. As we proceed to examine the role of supermassive black holes in these encounters, keep in mind that these massive entities also respond to and influence these grand cosmic feasts, adding yet another layer of complexity and fascination to the saga of galactic cannibalism. At the heart of nearly every large galaxy lies an enigmatic giant, known as a supermassive black hole. These colossal entities, with masses ranging from millions to billions of times that of our Sun, wield tremendous gravitational influence, shaping the very core of their host galaxies. But beyond their silent watch at the centers of galaxies, supermassive black holes play a dynamic, even dramatic role during galactic encounters. Their presence and activity can profoundly affect the choreography and consequences of these cosmic interactions. To appreciate the role of supermassive black holes in galactic encounters, it is first important to understand what these mysterious objects are. Unlike ordinary black holes formed from the collapse of massive stars, supermassive black holes reside at galaxy centers and grow by accreting gas, stars, and merging with other black holes. Their gravitational pull is so extreme that once matter crosses their event horizon, nothing escapes, not even light. Yet, paradoxically, the regions surrounding these black holes can shine incredibly bright due to the intense radiation emitted by infalling matter spiraling into the abyss. When galaxies collide and merge, their central black holes are destined to meet, initiating an extraordinary sequence of events. During the initial stages of a galactic merger, as gravitational forces disrupt gas clouds within both galaxies, vast reservoirs of gas and dust are funneled towards the nuclei. This inflow can ignite intense periods of black hole growth, transforming quiescent black holes into active galactic nuclei, AGN, that outshine entire galaxies. The enormous energy released during this accretion phase influences the surrounding galactic environment, regulating star formation by heating or expelling gas, a phenomenon astronomers refer to as feedback. As the merger progresses, the two supermassive black holes themselves begin to spiral closer under gravitational attraction, eventually forming a bound binary system at the core of the newly merged galaxy. This black hole duet continues to lose energy through interactions with surrounding stars, gas, and gravitational radiation, inching ever closer until they finally coalesce into a single, even more massive black hole. Such cataclysmic mergers of black holes are thought to be powerful sources of gravitational waves, ripples in the fabric of spacetime first predicted by Einstein and recently detected by facilities like LIGO and Virgo. The presence of supermassive black holes during galactic encounters also helps explain some of the complex morphological and dynamical changes observed post-merger. The gravitational forces imposed by these central behemoths can shape the distribution and motion of stars in the galaxy, influencing the development of dense stellar cores or elliptical morphologies often seen after major mergers. Moreover, the energy output from AGN can clear central regions of cold gas, quenching subsequent star formation and altering the evolutionary path of the galaxy. Intriguingly, observations have revealed correlations between the mass of a galaxy's central black hole and properties of the host galaxy, such as the velocity dispersion of stars in the bulge, known as the M-sigma relation. This tight connection suggests a coevolution driven in part by the merger processes that fuel black hole growth and simultaneously shape the galactic structure. Supermassive black holes also play a significant role in environments rich with galactic interactions, such as clusters. In these crowded cosmic neighborhoods, repeated mergers and interactions involving galaxies with active black holes contribute to the growth of central dominant galaxies, giants whose monstrous black holes exert vast influence over their surroundings. In our own Milky Way, the central supermassive black hole, Sagittarius A Aquarius, is relatively quiet today, but may have experienced phases of heightened activity in the distant past, potentially connected to previous accretion events triggered by minor mergers or infalling gas. Future interactions, such as the predicted collision with the Andromeda galaxy, promise to awaken these sleeping giants anew. Research into the interplay between galactic encounters and supermassive black holes remains an active frontier. Observatories like the Event Horizon Telescope are beginning to image the immediate environs of black holes, while gravitational wave detectors open a new window to study their mergers. Theoretical models and cosmological simulations increasingly incorporate detailed physics of black hole growth and feedback to understand their pivotal role in galactic evolution. In essence, supermassive black holes serve as both witnesses and agents of galactic cannibalism. Their gravitational power anchors the heart of galaxies, while their energetic outbursts influence star formation and galactic morphology. As galaxies feast upon each other, these dark titans respond, grow, and merge in turn, weaving their own tale in the cosmic feast. Next, we will turn our attention to a more intimate perspective by examining the local examples, the Milky Way's neighbors, and uncover the evidence of our own galaxy's cannibalistic past. Through this case study, the dance of galactic cannibalism becomes tangible, bridging the distant cosmos with our immediate cosmic neighborhood. Our home galaxy, the Milky Way, like many galaxies throughout the cosmos, carries within it a rich and revealing history of interaction, growth, and growth by cannibalism. Unlike many distant galaxies that astronomers observe as isolated or recently disturbed systems, the Milky Way presents an exceptional laboratory where detailed evidence for past and ongoing galactic cannibalism can be meticulously studied. By examining our cosmic neighborhood and the imprints left by absorbed companions, we gain unparalleled insights into the processes that shape galactic evolution. The Milky Way is not a solitary wanderer in space, but a dominant member of a complex system known as the Local Group, which contains over 50 known galaxies, ranging from large spirals like our own and the Andromeda galaxy to numerous smaller dwarf galaxies. These neighboring galaxies have not only shared cosmic origin, but also threaded fates, with many undergoing interactions influenced by the gravitational dominance of the Milky Way. Among these interactions, evidence strongly supports that the Milky Way has grown substantially through the accretion of smaller satellite galaxies over billions of years. This cannibalistic behavior manifests through various channels, and its signatures are encoded in the motions, chemical compositions, and spatial distributions of stars within the Milky Way's halo and disk. One of the most striking pieces of evidence comes from the discovery of stellar streams, narrow, elongated trails of stars arcing around the Milky Way. These streams represent the torn remnants of dwarf galaxies and star clusters tidally disrupted during close encounters and gradually assimilated into the Milky Way's structure. For example, the Sagittarius stream, a vast, looping stellar ribbon detected in multiple surveys, traces the remnants of the Sagittarius dwarf elliptical galaxy, which is in the process of being consumed by the Milky Way. Beyond stellar streams, the diverse population of globular clusters and stars with unique chemical fingerprints provides clues to past mergers. Certain globular clusters, tightly bound groups of stars orbiting the Milky Way, have origins linked to accreted dwarf galaxies. Their distinct elemental abundances and orbital properties differentiate them from clusters formed within the Milky Way itself. Galactic archaeology, the field that reconstructs a galaxy's past via stellar populations, has advanced rapidly through large-scale surveys such as the Sloan Digital Sky Survey and data from the Gaia Space Observatory. Gaia's unprecedented measurements of stellar positions, velocities, and distances have revealed the presence of multiple merger remnants, highlighting a complex history of minor mergers that have continuously shaped the Milky Way's halo. Among the notable merger events is the Gaia Enceladus, or Gaia Sausage Merger, thought to have occurred around 10 billion years ago. This major accretion is believed to have contributed a significant number of stars to the Milky Way's inner halo and influenced the structure of the thick disk, demonstrating how galactic cannibalism directly affected our galaxy's evolution. The large and small Magellanic clouds, two prominent irregular dwarf galaxies visible from the southern hemisphere, provide further evidence of ongoing interactions. These dwarf galaxies are close enough to be gravitationally bound to the Milky Way and exhibit signs of tidal deformation due to the Milky Way's influence. They, along with other smaller satellites, contribute gas, stars, and dark matter to the Milky Way, subtly reshaping its outskirts. Moreover, the dynamics of gas streams connecting the Magellanic Clouds and the Milky Way, known as the Magellanic Stream, reveal the complex interplay of gravity and hydrodynamics in a local cannibalistic context. These interactions drive gas inflows that can spark future star formation episodes within the Milky Way. The Milky Way's cannibalistic past is not solely about accumulation. It has consequences for its current structure and future evolution. The infall of smaller galaxies perturbs the galactic disk, induces star formation, and influences the orbits of stars and star clusters. It may even play a role in feeding the central supermassive black hole, further intertwining the threads of galactic evolution. Studying the Milky Way and its neighbors offers a uniquely detailed view of galactic cannibalism in action. While distant galaxies provide snapshots from eons past or glimpses of spectacular collisions, our neighborhood grants us both the breadth and resolution to decode the subtle complexities of accumulation and assimilation. As we continue our exploration, we will look closer at specific examples within our galactic environment, such as the ongoing consumption of the Sagittarius dwarf galaxy, revealing the intimate process of a galactic meal mid-journey. This case study enriches our understanding by connecting the universal processes of galactic cannibalism to the cosmic environment we inhabit. Nestled quietly in the southern skies, a small and faint companion to our Milky Way galaxy tells a vivid tale of cosmic interaction in real time. This is the Sagittarius dwarf spheroidal galaxy, or simply Sagittarius dwarf, a diminutive galaxy caught in the gravitational embrace of our much larger Milky Way, currently in the midst of a slow yet inexorable process of being consumed. It stands as one of the most compelling and well-documented examples of an ongoing galactic meal, where the Milky Way actively devours one of its neighbors. Discovered only in 1994, thanks to advancements in deep sky surveys and data analysis, the Sagittarius dwarf remained hidden until astronomers were able to discern its faint stellar populations against the backdrop of the Milky Way's dense star fields. What they uncovered was extraordinary, a satellite galaxy presently peeling apart under the overwhelming tidal forces exerted by the Milky Way's gravity. The Sagittarius dwarf lies roughly 70,000 light-years from Earth, well within our galactic halo, orbiting the Milky Way in a highly elliptical trajectory. Unlike more stable satellite galaxies that carefully dance around their host, Sagittarius dwarf is on a rapidly decaying orbit, having passed through the plane of the Milky Way multiple times over several 100 million years. Each passage inflicts substantial gravitational stress, pulling stars, gas, and dark matter from the dwarf and stretching them into long streams trailing across the sky. These stellar streams, the most prominent being the Sagittarius stream, arc around the Milky Way, spanning over 360 degrees in the sky. They are the telltale remnants of the galaxy in the process of disruption. Material torn from Sagittarius dwarf as it gradually loses cohesion and is assimilated into the Milky Way's halo. The discovery and mapping of this stream have been a defining achievement in astronomy, providing direct evidence of galactic cannibalism, not in some distant galaxy, but here in our cosmic backyard. By studying the velocities, chemical compositions, and spatial distribution of stars within the Sagittarius stream, astronomers glean insights into the history and dynamics of this ongoing merger. The stars originating from Sagittarius dwarf exhibit distinct patterns of heavy elements and ages, differing from native Milky Way stars. This chemical fingerprinting supports the conclusion that our galaxy grows, at least in part, by consuming smaller stellar systems. Moreover, observations indicate that the Sagittarius dwarf's interaction has influenced the Milky Way's structure itself. It may have induced ripples and disturbances in the outer galactic disk, perhaps even triggering episodes of star formation. This dynamic interplay underscores how galactic cannibalism is not a quiet, one-sided process, but a relationship with feedback and mutual effects. The eventual fate of Sagittarius dwarf is sealed. Models predict that within a few 100 million years, it will be thoroughly disrupted, its core shredded and absorbed, effectively ceasing to exist as an independent galaxy. This process exemplifies the gradual and majestic nature of galactic cannibalism, where even small galaxies succumb inexorably to the gravitational dominion of larger neighbors. The saga of the Sagittarius dwarf galaxy illuminates a profound truth about our own Milky Way. It is not a static entity, but rather a dynamic, evolving system shaped by continual interactions and growth. The slow consumption of Sagittarius dwarf offers a nearby window into the mechanisms that have sculpted galaxies across the cosmos for billions of years. As we move forward, we will broaden our view to other nearby companions like the Magellanic Clouds, examining their current roles and anticipated destinies within the Milky Way's vast gravitational influence. These neighbors further enrich the story of galactic cannibalism, demonstrating that our cosmic environment is a living, evolving stage for such timeless dramas. Positioned as some of the most luminous and conspicuous companions to our Milky Way, the large and small Magellanic clouds, LMC and SMC, serve not only as striking celestial features, but also as dynamic players in the ongoing story of galactic interactions. These irregular dwarf galaxies, visible from the southern hemisphere as glowing patches, offer a fascinating case study in the complex gravitational relationships galaxies share and pose profound questions about their own future fate within the Milky Way's vast influence. The Magellanic clouds are relatively close neighbors in cosmic terms. The Large Magellanic Cloud lies about 163,000 light-years away, while the Small Magellanic Cloud is slightly farther at roughly 200,000 light-years. Together, they are the largest and most massive satellite galaxies orbiting the Milky Way, brimming with star-forming regions and rich in gas and dust. Their ongoing dance with the Milky Way demonstrates the lingering effects of galactic cannibalism on a grand scale. These galaxies are thought to be gravitationally bound to each other, locked in an intricate orbital interaction that not only influences their internal dynamics, but also shapes their extended structures. Over billions of years, the Magellanic clouds have experienced their own mutual interactions, evident in the structural distortions, bursts of star formation, and the intricate bridges of gas connecting them. However, their relationship with the Milky Way is of particular interest. Observations suggest that the Magellanic clouds are currently making their first close approach to the Milky Way, although some debate exists around whether they have completed previous orbits or are recent arrivals. Their relatively high velocity and trajectory imply a complex future ahead. One dramatic manifestation of their interaction with our galaxy is the Magellanic Stream, a colossal ribbon of neutral hydrogen gas extending over 600,000 light-years trailing behind the clouds. This stream is a direct product of gravitational and hydrodynamic forces as the Milky Way's gravitational pull strips gas from the clouds during their orbital journey, a vivid example of tidal and ram pressure effects at work. The Magellanic Stream not only documents current interactions, but also fuels speculation about eventual accretion of this gas onto the Milky Way, potentially triggering new star formation. Looking ahead, astronomers predict that the Magellanic clouds will eventually succumb to the Milky Way's gravitational dominance, perhaps over the course of the next few billion years. This eventual fate is akin to a slow, magnificent banquet, where the Milky Way continues to grow by assimilating its substantial satellites. Over time, gravitational interactions will likely strip stars, gas, and dark matter from the Magellanic clouds, dispersing their contents into extended stellar streams and the diffuse halo of the Milky Way. This accretion process will subtly reshape the structure and composition of our galaxy, enriching it and possibly inducing dynamical effects such as warps or ripples in the galactic disk. Unlike the smaller Sagittarius dwarf, whose disruption is already well advanced, the Magellanic clouds are more robust and massive, set to persist longer before fully merging. Their infall and eventual consumption are anticipated to be among the most significant satellite accretion events in the Milky Way's future, with substantial astrophysical consequences. Moreover, the interaction may have profound implications for the Milky Way's central supermassive black hole. The inflow of gas as the Magellanic clouds lose mass could fuel accretion episodes, potentially stirring periods of active galactic nucleus activity, albeit on a modest scale relative to more violent mergers. The tale of the Magellanic clouds thus is one of motion, transformation, and cosmic destiny. They encapsulate the complex interplay of galaxies caught in mutual gravitational attraction, illustrating the multi-stage process of galactic cannibalism that spans vast epochs. By watching the Magellanic clouds, astronomers gain a living glimpse of the detailed dynamics shaping galaxy growth and interaction in the local universe. They teach us not only about cosmic history, but also about the future that awaits our own galactic home. As we proceed, we will expand our view to look at even larger, more famous galactic cannibals, monumental giants like M87 and the Andromeda galaxy, which showcase how similar processes play out on colossal, cluster-encompassing scales, shaping the universe's grandest structures. In the vastness of the cosmos, certain galaxies stand as monumental titans, colossal structures whose immense gravity and mass enable them to devour their smaller neighbors, thus earning the sobriquet galactic cannibals. Among these famous cannibals, M87 in the Virgo cluster, the Andromeda galaxy in our local group, and other giants provide extraordinary insights into the scale, mechanics, and consequences of galactic cannibalism on cosmic stages both near and far. M87, a gargantuan elliptical galaxy residing at the heart of the Virgo cluster, approximately 53 million light-years away, is one of the most spectacular examples of a galactic cannibal. Weighing in at over 1 trillion times the mass of our Sun, M87 dominates its locale through sheer gravitational force. This dominance allows it to capture and incorporate smaller galaxies in its vicinity, growing larger and more massive over billions of years. Astronomical observations of M87 reveal a smooth, enormous stellar halo extending hundreds of thousands of light-years, enriched by stars and globular clusters stripped from lesser galaxies. Deep imaging uncovers faint tidal debris and streams, remnants of ancient mergers acting as cosmic relics of past cannibalistic episodes. Additionally, M87 harbors one of the most massive known supermassive black holes recently imaged by the Event Horizon Telescope, signifying a long history of growth driven by repeated mergers and accretion. The central location of M87, within the Virgo cluster, places it amid a crowded neighborhood where galaxies frequently interact. This environment fosters numerous collisions and mergers, with M87 acting as a gravitational sinkhole, assimilating mass and reinforcing its status as a cosmic behemoth. The continuous buildup through galactic cannibalism plays a crucial role in the evolution of such massive central cluster galaxies. Switching focus to a galaxy much closer to home, the Andromeda galaxy, also known as M31, is the Milky Way's nearest large neighbor and a prominent example of galactic cannibalism in our cosmic backyard. Situated about 2.5 million light-years away, Andromeda is a massive spiral galaxy, slightly larger than the Milky Way, exhibiting clear signs of interaction and consumption of smaller satellite galaxies. Astronomers have identified numerous stellar streams, shells, and satellite galaxies around Andromeda that are signatures of ongoing and past mergers. One of the most notable is the Giant Stellar Stream, an enormous structure made up of stars torn from a companion galaxy, now assimilated into Andromeda's halo. This stream extends tens of thousands of light-years and is evidence of Andromeda actively feasting on its smaller neighbors. The detailed mapping of Andromeda's surroundings through surveys like the Pan-Andromeda Archaeological Survey, PANDAS, has revealed a complex web of tidal debris and satellite galaxies, underscoring a rich history of galactic cannibalism. Moreover, merger events in Andromeda have played a part in shaping its structure, possibly explaining its prominent bulge and diverse stellar populations. Astronomers also anticipate a dramatic future involving Andromeda and the Milky Way, a coming collision predicted to occur roughly 4 billion years from now. This impending merger between two giant galaxies represents one of the most significant cosmic cannibalistic events expected in our local universe, fundamentally reshaping both galaxies. Beyond M87 and Andromeda, Many other giant galaxies in clusters and groups partake in cannibalistic feasts. Central dominant galaxies, or CD galaxies, at the cores of rich clusters often grow to enormous sizes through the accretion of numerous smaller systems. Evidence of these mergers spans from spectacular tidal tails, visible in deep images, to complex velocity patterns of stars and globular clusters. Famous interacting systems like the Whirlpool Galaxy, M51, and the Antennae Galaxies, NGC 4038-4039, display dramatic collisions and are laboratories to study the physics underlying galactic cannibalism. In these systems, astronomers witness bursts of star formation, the stirring of gas, and the progressive blending of stellar populations, all hallmarks of the cannibalistic process. The grand scale of these famous cannibals exemplifies how galaxy formation and growth are profoundly driven by mergers and accretion. From solitary giants quietly absorbing dwarfs to colossal cluster centers dominating their environment, galactic cannibalism is an essential engine of cosmic evolution. Looking ahead, we will explore how modern technology, particularly supercomputers, enables astronomers to simulate these complex galactic interactions. By modeling cosmic feasts digitally, we better understand the mechanics and timelines of galaxies eating each other, enriching our comprehension beyond observational snapshots alone. The universe, vast and majestic, unfolds in ways often too grand and complex for direct observation alone to unravel. Much of what we understand about galactic cannibalism, the intricate processes by which galaxies engage, collide, and merge, has been illuminated by the power of supercomputers. These computational marvels allow astronomers to simulate cosmic feasts with increasing sophistication, bridging gaps in knowledge and revealing the dynamic choreography of galaxies over billions of years. At first glance, the idea of simulating galaxies, entities each containing billions to trillions of stars, clouds of gas and dust, and enveloped by vast dark matter halos, may seem an insurmountable computational challenge. Yet, advances in computational astrophysics over the past several decades have turned this challenge into an extraordinary opportunity. Simulating galactic collisions involves numerically solving the laws of physics, Newtonian gravity, hydrodynamics, radiative processes, and, increasingly, relativistic effects, in 3 dimensions over extended periods. Early attempts in the 1970s and 1980s used relatively simple calculations and limited resolution. However, they already demonstrated that tidal tails, bridges, and mergers could naturally arise from gravitational interactions, confirming hypotheses gleaned from telescope observations. Today, state-of-the-art supercomputer simulations incorporate millions to billions of particles, each representing massive collections of stars, parcels of gas, or elements of dark matter. These particles interact according to gravitational laws and include gas physics to account for star formation, supernova feedback, and black hole accretion. One fundamental tool in these simulations is the N-body algorithm, which calculates gravitational forces between all particles. However, given the astronomical number of particles in a full galaxy, direct force calculation between every pair would be computationally prohibitive. Instead, sophisticated techniques, such as tree algorithms and particle mesh methods, approximate forces efficiently while maintaining accuracy. Coupled with N-body dynamics, smoothed particle hydrodynamics (SPH) approaches are used to model the behavior of interstellar gas. These techniques allow simulations to capture how gas clouds collapse to form stars, dissipate energy through radiation, and accumulate around black holes, all vital for reproducing realistic galaxy evolution. Simulating a galactic collision begins by setting the initial conditions, positioning 2 or more galaxies in space with specified masses, structures, velocities, and orientations. Researchers can vary parameters to explore how different merger scenarios play out, from head-on, violent collisions to gentle, grazing encounters. As the simulation runs, it visualizes the gravitational tug-of-war pulling the galaxies together, tidal forces drawing out extended tails of stars and gas, and the eventual merging of stellar populations. Gas compressed during these interactions ignites bursts of star formation, while central regions can fuel supermassive black holes, often triggering energetic feedback. These simulations offer remarkable insights. For instance, they illuminate how spiral galaxies can transform into elliptical galaxies through major mergers, redistributing stars into randomized orbits and depleting gas reservoirs. They reveal the timescales involved in cannibalism, showing that mergers can span 1 billion years or more, from initial contact to full assimilation. Supercomputer simulations have also been instrumental in interpreting observational data. By comparing simulation outputs with images and spectra from telescopes, astronomers validate their models and refine understanding of complex phenomena. This synergy sharpens predictions, guiding where to look for tidal remnants, stellar streams, or signs of black hole activity in real galaxies. Beyond individual mergers, cosmological simulations extend to much larger volumes, modeling the formation and evolution of thousands of galaxies within the expanding universe. These grand-scale simulations, such as Illustris and Eagle, demonstrate how galactic cannibalism operates on population levels, shaping the mass distribution, morphological diversity, and large-scale structures like galaxy clusters and the cosmic web. Moreover, these computational ventures contribute to unraveling the mysteries of dark matter, testing how different dark matter models impact the behavior of halos and consequent mergers. Improved resolution, more sophisticated physics, and increasing computational power continue to drive this field forward. Fundamentally, simulating galactic collisions exemplifies humanity's quest to comprehend the universe, not just by observing, but by recreating cosmic realities within silicon and code. These virtual cosmic feasts reveal the delicate interplay of gravity, gas dynamics, and star formation that govern galactic cannibalism's slow but profound dance. As our exploration continues, we will delve deeper into the internal stellar dynamics within merging galaxies. The chaos and reorganization that ensue during these encounters shape the newborn galaxy's structure and future. An evolutionary tale told through the motions of stars, the power of gravity, and the echoes of ancient cosmic feasts. Within the seemingly serene night sky, galaxies silently whirl and evolve over cosmic epochs. Yet beneath their tranquil facade lies a realm of dynamic turmoil, especially during galactic mergers, vast cosmic events marked by intricate gravitational dances, chaos, and profound reorganization of stars. To truly appreciate galactic cannibalism, it's essential to uncover the fascinating processes governing stellar dynamics within merging galaxies, where billions of stars interact through gravity, reshaping the cosmos itself. When two galaxies begin their gravitationally bound embrace, their internal stellar populations experience profound and often chaotic disturbances. Unlike fluid collisions in everyday life, these interactions among stars aren't direct physical crashes. Stars are separated by tremendous distances and thus rarely collide. Instead, stars respond to shifting gravitational potentials, their orbits altered dramatically by the evolving mass distribution. The gravitational forces during a merger act like unseen sculptors, pulling, stretching, and twisting stars into new trajectories. Initially, each galaxy's well-ordered rotation or dispersion-dominated motions become unstable. In spiral galaxies, the familiar symmetric disks warp, spiral arms become distorted, and dense central bulges are stirred. The orbits of stars become more randomized, slowly transforming disk galaxies into more spherical or ellipsoidal shapes, typical of elliptical galaxies formed after major mergers. Tidal forces stretch stars into spectacular features such as tidal tails and bridges, wispy extensions containing stars flung far from their original homes. These structures can span hundreds of thousands of light-years, acting as visible markers of gravitational chaos. The process of violent relaxation plays a central role here. Coined by astrophysicist Donald Lynden Bell in the 1960s, violent relaxation describes how, during the rapid change in gravitational potential caused by the merger, stars redistribute their kinetic energies and spatial positions, quickly settling into new equilibrium configurations. This reorganization leads to a stable, merged galaxy, where the memory of the progenitor's ordered motions is largely erased. Yet this violent relaxation is complex and non-uniform. Some stars plunge deep into the merger remnant's core, contributing to dense central regions. Others are ejected into extended halos, or even flung into intergalactic space as intruder stars, lonely travelers forged from cosmic violence. Gas plays a crucial but somewhat distinct role during these dynamical transformations. Unlike stars, gas clouds can collide, dissipate energy through radiation, and cool. During mergers, gravitational torques funnel gas towards the central regions, where it compresses and fuels bursts of star formation known as starbursts. The inflow of gas can also feed central supermassive black holes, igniting luminous active galactic nuclei that may regulate further evolution through energetic feedback. Within the background of this complex stellar and gaseous interplay, dynamical friction acts as a critical mechanism. As smaller galaxies or dense stellar clumps orbit within a larger system during the merger, gravitational interactions with the surrounding field of stars and dark matter slow their motion, causing them to lose energy and spiral inward toward the galactic center. This process enables the eventual coalescence of galactic nuclei and central black holes, vital elements in the final stages of the merger. Merging galaxies therefore transition from ordered, rotationally supported systems to dispersion-supported remnants. The end product is often an elliptical galaxy, where stars exhibit randomized orbits and new structural features emerge from the chaotic past. However, not all mergers yield identical outcomes. The specific orbital configurations, mass ratios, gas content, and initial galactic morphologies highly influence the details of stellar dynamics and the speed of relaxation. For example, minor mergers perturb the larger galaxy's disk to a lesser degree, inducing subtle kinematic changes, while major mergers induce drastic reorganization and morphological transformations. Modern instruments and surveys, such as the Gaia mission, enable astronomers to trace the motions of individual stars in and around the Milky Way, revealing the relics of past mergers imprinted as streams and substructures with distinct kinematic signatures. These findings corroborate theoretical predictions on how stellar populations reorganize during galactic cannibalism. Numerical simulations further elucidate these processes, revealing not only the chaotic dance of stars, but also how this chaos fosters cosmic creativity, triggering new structures, redistributing angular momentum, and igniting fresh stellar birth. In essence, stellar dynamics during galactic mergers is a tale of chaos transforming into order, a fundamental story of destruction and creation woven into the cosmic fabric. This intricate ballet helps explain the diversity of galactic forms observed today and underscores the transformative power of galactic cannibalism in shaping the universe. As we continue our exploration, we will next delve into how these dramatic stellar rearrangements affect the birth and death of stars, exploring the delicate balance between star formation bursts and quenching in the aftermath of mergers. In the grand cosmic theater of galactic cannibalism, amid swirling masses of stars and clouds of gas, lies a potent narrative of creation and extinction, the birth and death of stars. These stellar cycles are profoundly influenced by the cosmic feasts taking place when galaxies interact, collide, and merge. Understanding how star formation is both ignited and quenched during such dynamic events is crucial to grasp the lasting impact of galactic cannibalism on galaxy evolution. At the heart of star formation lie vast reservoirs of cold molecular gas, primarily hydrogen, scattered throughout galactic disks or clumped in enormous clouds. Under the right conditions, these clouds collapse under gravity, leading to the formation of new stars. Galactic interactions, especially mergers, dramatically alter these conditions, sometimes acting as cosmic catalysts that fuel intense bursts of star creation. When two galaxies approach and interact, their gravitational potentials overlap and fluctuate. This interaction compresses gas clouds, triggers shocks, and funnels gas toward central regions. Dense gas concentrations become prime sites for rapid star formation, known as starburst events. These bursts can elevate the galaxy's star formation rate by orders of magnitude, outshining typical quiescent galaxies. The antennae galaxies provide dramatic examples of this process, where spectacular collisions have triggered bright knots of newly formed stars within tidal tails and galactic centers. On smaller scales, even minor mergers or close flybys can perturb gas clouds, sporadically triggering star formation. However, galactic collisions don't always lead to star birth. In some cases, they suppress or quench star formation. This paradox arises due to complex feedback mechanisms. The intense starburst itself produces energetic stellar winds and supernova explosions, injecting energy into the surrounding gas, heating it and disrupting star-forming clouds. Similarly, active galactic nuclei, energized by supermassive black holes fed during mergers, emit powerful jets and radiation that can expel gas or prevent it from cooling effectively stalling star formation. In some massive mergers, the cumulative feedback can clear or heat much of the cold gas, starving the galaxy of the raw material needed to form new stars. This suppression contributes to the transformation of star-forming spiral galaxies into more quiescent elliptical galaxies, rich in old stars with little ongoing formation. The interplay between star formation triggering and suppression creates a temporal and spatial mosaic within merging galaxies. Regions undergoing starbursts might exist alongside zones where star formation is winding down or temporarily halted. Over millions to billions of years, these processes sculpt the galaxy's stellar population, affecting its color, brightness, and evolution. Beyond immediate mergers, repeated episodes of minor accretions introduce fresh, sometimes metal-poor gas that can rejuvenate star formation in large galaxies, demonstrating the nuanced impact of galactic cannibalism across timescales. Astronomers employ observations across the electromagnetic spectrum, from ultraviolet tracing young, hot stars to infrared mapping dust-enshrouded star-forming regions, to piece together how mergers affect star birth. These observations, coupled with simulations, reveal how galaxies walk a delicate line between creation and destruction during their cosmic meals. Thus, the birth and death of stars within interacting galaxies is a story of tumultuous balance, where gravitational encounters kindle stellar nurseries while powerful feedback can quench these processes, marking an intricate evolutionary dance. This dance not only shapes individual galaxies, but also seeds the universe with the materials essential for planets and life. Following this theme, our next segment will delve into the growth of central black holes during mergers, how these enormous gravitational wells feed and influence their host galaxies in spectacular feeding frenzies, further connecting the intricate web of galactic evolution. At the heart of nearly every massive galaxy resides a supermassive black hole, colossal entities millions to billions of times the mass of our Sun. These enigmatic giants possess gravitational fields so intense that nothing, not even light, can escape once crossing their event horizons. While often dormant, their activity can dramatically flare during galactic mergers, leading to what astronomers describe as feeding frenzies, periods when black holes voraciously consume matter and profoundly influence their host galaxies' evolution. When two galaxies begin their gravitational dance toward merger, tidal forces funnel vast streams of gas and dust towards the galactic centers. These inflows feed the central black holes, causing them to transition from relatively quiescent states to active galactic nuclei, AGN. During these active phases, the black holes accrete matter at immense rates, converting gravitational energy into powerful radiation and energetic jets observable across the electromagnetic spectrum. This feeding frenzy is not only a spectacular display, but also plays a pivotal role in the merger process. As the black holes consume gas, they can release enormous amounts of energy into their surroundings. This energy manifests as intense radiation pressure, powerful outflows, and relativistic jets ejecting particles at near light speed. Such feedback mechanisms can regulate star formation by heating or expelling the gas reservoirs necessary for new stars, thus quenching future stellar birth in the merged galaxy. Additionally, mergers are believed to accelerate the growth of supermassive black holes by bringing together the central black holes from the progenitor galaxies. As the galaxies coalesce, their black holes sink to the common center through dynamical friction, eventually forming a closely bound binary system. Over time, these binaries lose orbital energy through interactions with surrounding stars, gas, and gravitational radiation, culminating in a cataclysmic merger that produces even more massive black holes and a burst of gravitational waves. Astrophysical observations support this framework. Many luminous quasars and AGN observed at high redshifts, the distant universe, are often associated with galaxies experiencing mergers or interactions, highlighting the link between galactic collisions and black hole activity. Similarly, local examples reveal active nuclei in galaxies with disturbed morphologies or tidal features, providing compelling evidence of merger-induced feeding episodes. Simulations of galaxy mergers incorporating detailed black hole physics further elucidate these complex processes. They show how gas dynamics funnel material toward the nucleus, igniting starbursts and black hole growth simultaneously. By modeling feedback effects, simulations reproduce observed galaxy properties, such as the correlation between black hole mass and the velocity dispersion of stars in the galactic bulge, known as the M-sigma relation, indicating co-evolution. In essence, the feeding frenzies of supermassive black holes during galactic mergers represent a transformative stage in galaxy evolution. These events mark both a phase of spectacular cosmic energy release and a critical regulator of the interplay between black hole growth and star formation. Understanding these feeding frenzies deepens our grasp of how galaxies reshape themselves through mergers and feeds into larger narratives about the cosmic life cycle. Our next adventure will dive into galactic archaeology, where we explore how astronomers decode merger histories by examining stellar populations, celestial fossils that chronicle the grand feasts of galaxies past. In the vast expanse of the universe, galaxies silently hold the chronicles of their turbulent pasts deep within their stars. This cosmic storytelling is the essence of galactic archaeology, a field dedicated to unearthing the histories of galaxies by studying the properties of their stellar populations. Like skilled human archaeologists, Astronomers sift through these celestial fossils to decipher the long and often dramatic tales of galactic mergers, cannibalism, and evolution. Every star in a galaxy is a time capsule, carrying within it the chemical and dynamical imprint of its birthplace and the environment it has traversed. When galaxies collide and merge, their stars intermingle, but not without leaving distinctive traces. By examining these stellar populations, patterns in star ages, metallicities, chemical compositions, spatial distributions, and orbital motions, galactic archaeologists reconstruct merger events that often occurred billions of years ago. One of the fundamental tools in this investigative endeavor is the analysis of stellar kinematics. Stars that formed in the original galaxy typically exhibit orderly orbital motions, such as the rotation of a galactic disk. In contrast, stars accreted from disrupted satellite galaxies or mergers tend to follow more chaotic or eccentric orbits. By mapping the velocities and positions of stars, astronomers identify coherent structures like stellar streams, shells, and overdensities that betray their extragalactic origins. Chemical abundances provide another powerful clue. Elements heavier than helium, collectively termed metals in astronomy, are produced inside stars and distributed through supernova explosions. Thus, the metal content of stars reveals their formation environment and history. Stars originating in dwarf galaxies often show lower metallicities and unique elemental ratios compared to stars born in massive hosts like the Milky Way. Detecting these chemical fingerprints allows researchers to differentiate between indigenous and accreted populations. Modern telescopes and instruments have revolutionized galactic archaeology. Surveys such as the Sloan Digital Sky Survey, SDSS, and missions like the European Space Agency's Gaia satellite provide precise measurements of stellar positions, distances, motions, and spectra, enabling astronomers to tease apart the complex assembly history of galaxies with unprecedented detail. For instance, Gaia's detailed mapping of the Milky Way's stars has unveiled a rich tapestry of past mergers. One remarkable discovery is the Gaia Enceladus, or Gaia sausage event, a significant merger that contributed a substantial population of stars to the Milky Way roughly 10 billion years ago. This merger reshaped the inner halo and thick disk, representing a transformational chapter in our galaxy's growth. In addition to the Milky Way, similar approaches apply to nearby galaxies such as Andromeda, where deep observations reveal fossil records of multiple accretion events. These findings confirm that galactic cannibalism is a common and ongoing mechanism driving galactic evolution across the universe. Galactic archaeology also addresses broader questions. How do merger rates vary over cosmic time? What role do minor versus major mergers play in assembling massive galaxies? How are dark matter halos affected by these processes? Through the fossil record encoded in stars, astronomers gain insights that complement theoretical models and cosmological simulations. In sum, galactic archaeology transforms galaxies into storytellers, narrating the saga of cosmic cannibalism through the language of their stars. As we delve deeper into this field, we unlock the secrets of past mergers, enabling a more profound understanding of how the grand tapestry of the universe is woven. Next, we will explore the chemical fingerprints left behind by galactic mergers and how these subtle signatures help astronomers trace the complex compositional changes that galaxies endure as they feast on one another. Galaxies, vast conglomerates of stars, gas, dust, and dark matter, carry within their luminous and diffuse components intricate chemical histories. These stories, etched into the very elements forged in stars and supernovae, serve as cosmic fingerprints, revealing the complex processes that shape and reshape galaxies over billions of years. One of the most profound influences on a galaxy's chemical composition is the process of galactic mergers, the cosmic events where two or more galaxies collide, interact, and often combine into a new entity. Understanding how these mergers alter galactic chemistry provides crucial insights into galaxy evolution and the broader workings of the universe. At the heart of galactic chemistry lie elements heavier than hydrogen and helium, collectively known as metals by astronomers. These metals are synthesized in the hearts of stars during nuclear fusion processes and expelled into the surrounding interstellar medium through stellar winds and explosive supernovae. Over time, this enrichment process gradually increases the metallicity, the abundance of heavy elements of a galaxy's gas and stars, fueling the formation of new stars and planets with increasingly complex compositions. When two galaxies merge, their stellar and gaseous components mix in complex ways, profoundly affecting their combined chemical profiles. Mergers bring together stellar populations of different ages, origins, and metallicities. For example, a massive spiral galaxy, rich in metals and with a relatively mature population of stars, may merge with a smaller, metal-poor dwarf galaxy. The infall of this chemically distinct material can dilute or enrich the larger galaxy's metallicity, depending on the balance of masses and compositions. The gas reservoirs of the merging galaxies play a central role in chemical evolution during and after the merger. Collisions can compress gas clouds, triggering intense bursts of star formation, known as starbursts, that rapidly convert gas into new stars. This sudden increase in star formation accelerates the cycling of material and the enrichment of the interstellar medium, injecting fresh metals and altering the chemical landscape. Moreover, the violent dynamics of a merger can redistribute gas and metals throughout the merged system. Tidal forces and shocks lift gas from galactic centers into extended tails and halos. These structures may carry chemically enriched material far from the sites of star formation, creating gradients in metallicity and causing diversity in stellar populations across the galaxy. Active galactic nuclei, AGN, fueled by gas driven toward central supermassive black holes during mergers, can also influence chemical evolution. The energetic outflows and jets launched by AGN feedback can expel metal-rich gas from galaxies, regulating star formation and altering the chemical inventory of both the host galaxy and the surrounding intergalactic medium. Astronomical spectroscopy offers a window into these complex chemical changes. By analyzing light from stars, gas clouds, and nebulae in merging galaxies, astronomers can measure abundances of key elements like oxygen, iron, carbon, and nitrogen, and decipher the enrichment history. Observations reveal patterns such as enhanced alpha element abundances indicative of rapid star formation, or distinct metallicity gradients shaped by merger-induced gas flows. Studies of nearby interacting systems, like the antennae galaxies, show spatial variations in chemical composition linked to merger-driven starbursts and gas redistribution. Similarly, analyses of elliptical galaxies, which are often merger remnants, unveil complex chemical signatures that reflect their assembly histories and the cumulative effects of past mergers. On larger scales, galactic mergers contribute to the chemical evolution of galaxy clusters and the intergalactic medium. Metals ejected during mergers enrich the space between galaxies, influencing future generations of galaxies and cosmic structures. In essence, chemical fingerprints provide a detailed record of galactic cannibalism's transformative impact. They allow astronomers to trace star formation histories, merger events, and feedback processes that define the life cycles of galaxies. Understanding these chemical alterations not only enriches our knowledge of mergers, but also offers a broader view of cosmic evolution. how matter cycles through stars and galaxies, building complexity across the universe. In the following chapter, we will examine the role of dark matter halos during and after galactic cannibalism, exploring how these elusive yet dominant structures influence the dynamics and ultimate fate of merged galaxies. Dark matter halos, the invisible scaffolding enveloping galaxies, play a pivotal role in shaping the destiny of galactic cannibalism. Though unseen by traditional telescopes, these halos, comprised of mysterious, non-luminous matter, constitute the majority of a galaxy's mass and govern its gravitational landscape. As galaxies engage in gravitational feasts, the interactions and transformations of their dark matter halos become crucial to understanding how these cosmic assimilations unfold and what remains long after the visible fireworks subside. Every galaxy resides within an extensive dark matter halo that extends far beyond its luminous stars and gas. These halos provide the gravitational well that holds galaxies together, influencing their rotational velocities and their interactions with neighbors. When two galaxies approach each other, it is first their dark matter halos that respond. Halos begin to overlap, merging, and interact well before the galaxy's visible components make contact. During galactic cannibalism, the dark matter halos undergo a complex dance of tidal stripping, merging, and reorganization. As the smaller galaxy ventures into the larger halo, its own dark matter is gradually drawn away by tidal forces, forming elongated streams or clouds of dark matter trailing behind the infalling system. This stripping reduces the mass of the smaller galaxy, weakening its gravitational coherence and accelerating its assimilation. The merger ultimately leads to the coalescence of the two halos into a single, more massive dark matter structure enveloping the merged galaxy. This process influences the dynamics of the merger, the efficiency of star formation, and the structural properties of the resultant system. For example, the shape, density profile, and substructure of the combined halo affect how gas cools and condenses, which in turn modulates the galaxy's evolutionary path. Post-merger, the dark matter halo continues to evolve. It may retain remnants of disrupted subhalos, smaller lumps of dark matter, originating from the devoured galaxies. These subhalos are the hidden architects of satellite galaxies and stellar streams seen around massive galaxies today. Their positions and motions trace the recent merger history and enrich our understanding of the hierarchical nature of cosmic structure formation. The behavior of dark matter halos during cannibalism also helps explain phenomena such as the distribution of globular clusters, the morphology of extended stellar halos, and observed gravitational lensing effects, where massive halos bend light from distant background sources. These observations serve as indirect evidence of the dark matter's crucial role during and after mergers. Modern cosmological simulations incorporate sophisticated dark matter physics alongside gas dynamics and stellar processes to model these mergers realistically. They predict how halos grow through successive mergers, how substructure evolves, and how the interplay between dark matter and baryonic matter shapes galactic properties. These models align impressively with observations, affirming the central importance of dark matter halos in galactic cannibalism. Understanding halo dynamics is also essential for interpreting the large-scale structure of the universe. The cosmic web, a vast network of interconnected filaments and voids shaped predominantly by dark matter, facilitates the inflow of galaxies into clusters where cannibalism is most prevalent. Here, dark matter halos merge to build the most massive structures known. Ultimately, the impact of galactic cannibalism on dark matter halos is a story of transformation and growth. Halos merge, reshape, and seed future cosmic interactions, underpinning the unending cycle of galaxy formation and evolution. As we now turn our gaze to the fate of merged galaxies themselves, we explore how these cosmic feasts translate into the diversity of galactic forms, ellipticals, spirals, and the sequence astronomers have long studied, from the aftermath of cannibalism to the grand observable structures we see across the universe. As galaxies engage in cosmic encounters and mergers, their fates unfold in a remarkable variety of ways, giving rise to the diverse population of galaxies we observe across the universe. Understanding the ultimate outcomes of mergers leads us to the heart of the famous Hubble sequence, a classification framework that organizes galaxies by their shapes and structures into ellipticals, spirals, and lenticulars. In this section, we explore how galactic cannibalism molds galaxies into these forms and shapes their long-term evolution. The Hubble sequence, first proposed by Edwin Hubble in the 1920s, arranges galaxies primarily into three morphological classes: ellipticals, characterized by smooth ellipsoidal light distributions with predominantly old stars; spirals, noted for their flat, rotating disks with spiral arms and active star formation; and lenticulars, which exhibit properties intermediate between ellipticals and spirals. While initially designed as a heuristic tool, this classification also hints at evolutionary pathways shaped, in no small part, by mergers and interactions. When two galaxies merge, the relative masses, gas content, and dynamics of the progenitors dictate the morphology of the resulting remnant. Major mergers between two gas-rich spiral galaxies tend to be particularly transformative. The intense gravitational forces disrupt the ordered disk structures, randomize stellar orbits, and often funnel large amounts of gas toward the center, triggering starbursts and feeding central black holes. The turbulent aftermath frequently results in the emergence of an elliptical galaxy, a spheroidal system dominated by older stars in randomized orbits, with little cold gas left to fuel new star formation. These elliptical galaxies are typically redder, more massive, and dynamically hot systems, the end products of violent mergers and cannibalism. Their smooth appearance, contrasted with the ordered spirals, reflects the profound dynamical reorganization driven by the merger. Alternatively, mergers involving at least one gas-poor or less massive galaxy, or sequences of minor mergers, can produce lenticular galaxies, S-Eroids. These galaxies have disk-like structures, but show little ongoing star formation, with features suggesting faded spirals that lost gas and were heated dynamically through interactions. Interestingly, not all mergers destroy spiral structures. If gas fractions are sufficiently high and the mergers occur under specific conditions, such as particular orbital geometries, disks can survive or reform after the merger. This process explains how some spiral galaxies, including our own Milky Way, maintain or rebuild their disk morphology despite a history peppered with past mergers and cannibalism. The detailed outcomes depend on a complex interplay of factors, including the angle and velocity of collision, the presence and distribution of dark matter halos, feedback processes from star formation and black hole activity, and the inflow or removal of gas during the merger. Observations of distant galaxies across cosmic time reveal that major mergers were more common in the early universe, contributing significantly to the buildup of the massive elliptical galaxy population. In contrast, the relative quiet of the local universe sees more frequent minor mergers and accretion events, allowing many spirals to persist or regrow their disks. Simulations that incorporate realistic physical processes confirm these evolutionary pathways and help interpret observations within the Hubble sequence framework. They demonstrate the viability of disk survival and the formation of ellipticals, underscoring the crucial role of mergers in shaping galactic morphology. Ultimately, the fate of merged galaxies underlines how galactic cannibalism is a fundamental engine driving the cosmic diversity of forms. From majestic ellipticals to resilient spirals, the ongoing dance of mergers sculpts the tapestry of the universe. As we look forward, the predicted collision between the Milky Way and Andromeda promises to be a spectacular and instructive example, further illuminating the intricate destinies galaxies traverse in their cosmic journey. Looking up into the night sky, we see the familiar glow of the Milky Way, our cosmic home amid billions of galaxies. Yet beyond this serene vista lies an extraordinary tale not only of distant epochs, but of a future event that will dramatically reshape our galactic neighborhood. The predicted collision between the Milky Way and its giant neighbor, the Andromeda Galaxy. This impending cosmic encounter offers a powerful, tangible example of galactic cannibalism in action, and provides a glimpse into the dynamic fate awaiting our galaxy. The Andromeda Galaxy, also known as M31, shines as the nearest large spiral galaxy to the Milky Way, approximately 2.5 million light-years away. It is slightly larger than our own galaxy, containing an estimated 1 trillion stars compared to the Milky Way's several hundred billion. Despite this vast distance, astronomers have determined through precise measurements of celestial motions that Andromeda and the Milky Way are on a collision course, inexorably drawing closer under their mutual gravitational attraction. Current data suggest that in about 4 billion years, these two massive spiral galaxies will begin a slow, majestic merger. Rather than a quick or violent crash, as might be imagined, this cosmic event will unfold over billions of years. The Milky Way and Andromeda will first approach each other, initiating tidal distortions as gravitational forces reach across intergalactic space, stretching stars and gas into elongated streams. As they pass near, the galaxies will undergo several close encounters, each triggering bursts of star formation by compressing vast clouds of interstellar gas. Over time, dynamical friction, the gravitational drag resulting from interactions between stars and dark matter halos, will cause the galaxies to lose orbital energy and spiral closer, eventually merging into a single, more massive galaxy. Simulations of this event predict the resulting galaxy will be an elliptical or lenticular type, lacking the structured spiral arms familiar to us. The complex new gravitational potential will randomize stellar orbits, and much of the gas will be consumed in starbursts or expelled by energetic feedback processes, marking the end of an era for the spiral forms of both progenitors. Importantly, despite the vast number of stars in both galaxies, the enormous distances between individual stars mean direct stellar collisions will be exceedingly rare. However, the shifting gravitational landscape will profoundly alter star orbits, potentially ejecting some stars into intergalactic space and reshaping the stellar halo. The collision will also spur activity in the supermassive black holes residing at the centers of each galaxy. As gas is funneled inward during the merger, the black holes are expected to accrete material vigorously, shining as luminous active galactic nuclei for millions of years. Eventually, these black holes themselves will coalesce, emitting powerful gravitational waves rippling through space-time. This colossal galactic dance holds profound implications beyond physics and astrophysics. It exemplifies the natural processes shaping the universe's large-scale structure, the growth and transformation of galaxies, and the inevitability of change across cosmic timescales. For future inhabitants of our solar system, the sky will become a spectacular theater of light and motion, with Andromeda growing larger and eventually merging with the Milky Way, rewriting the night sky's patterns and beauty. In contemplating this cosmic destiny, we appreciate that galactic cannibalism is not a distant or abstract concept, but a dynamic, ongoing reality shaping our universe, including the very galaxy we call home. As we proceed, we will widen our lens further to explore how galactic cannibalism has unfolded across cosmic history, influencing galaxy evolution from the early universe to the present day. Galactic cannibalism is not a phenomenon confined to the relatively local or recent cosmos. It is a process woven into the very fabric of universal evolution, influencing galaxy formation and growth across the vast stretches of cosmic time. To understand its frequency and impact in the early universe, we must look back billions of years, peering into a more chaotic, energetic epoch when galaxies were forming, assembling, and interacting with fervent intensity. The early universe, following the Big Bang roughly 13.8 billion years ago, was a hot, dense, and rapidly expanding cosmic expanse. As it cooled, matter began forming the first structures under the influence of gravity, with dark matter halos emerging as gravitational wells to collect gas and spawn the first protogalaxies. These primordial systems were typically small, irregular, and rich in cold gas, lacking the organized forms characteristic of mature galaxies. During this epoch, the cosmic landscape was densely populated with numerous small galaxies clustered close together. The proximity of these building blocks, combined with their gravitational interactions, led to frequent mergers and accretion events. As a result, galactic cannibalism was a dominant mechanism driving the assembly of massive galaxies. These early universe mergers helped build up the large and complex galaxies we observe today by combining smaller progenitors over successive generations. Observationally, astronomers harness powerful telescopes like the Hubble Space Telescope and, more recently, the James Webb Space Telescope to look deep into space and thus back in time. They observe that distant galaxies, whose light has traveled billions of years, exhibit disturbed morphologies, clumpy star formation, and signs of interactions more frequently than galaxies in the local modern universe. These features strongly imply a higher merger rate in the past, with galactic cannibalism playing a vital role during these formative periods. Quantitative studies confirm this, showing the merger rate peaks roughly between 6 and 10 billion years ago, coinciding with the cosmic noon, the period of peak star formation in the universe. This era witnessed a surge in major and minor mergers, which not only helped to assemble galaxies, but also triggered intense starburst activity and fueled the growth of supermassive black holes. The overarching cosmological framework, known as the hierarchical model of structure formation, supports this picture, positing that small structures form first and then merge to create larger systems. In this scenario, galactic cannibalism is an inherent and ongoing process, gradually sculpting the universe's large-scale structure. Simulations of the early universe reflect this paradigm, reproducing the observed frequency of mergers and the subsequent growth patterns of galaxies. These models reveal that early interactions were often more gas-rich and violent compared to present-day mergers, making them highly efficient at triggering starbursts and black hole growth. While mergers were prolific in the early universe, the nature of cannibalism evolved with cosmic time. As galaxies grew larger and gas reservoirs diminished, major mergers became less frequent, with minor mergers and satellite accretion dominating galaxy growth in later epochs. This evolution helps explain the morphological diversity and star formation trends observed across cosmic history. Furthermore, the chemical complexity and stellar populations of galaxies today bear the imprints of these ancient mergers. The study of stellar populations and chemical fingerprints allows astronomers to trace back merger histories even when direct observations of the early universe are impossible. In summary, galactic cannibalism was a fundamental and frequent process in the early universe, serving as a cosmic architect in the assembly and evolution of galaxies. Its dominance during the universe's youth laid the foundation for the grand structures and diverse galaxy populations we witness today. Our next journey will explore how these merging galaxies collectively shaped larger cosmic architectures, influencing the formation of galaxy clusters and the cosmic web that spans the universe. The universe on its largest scales reveals a breathtaking cosmic tapestry, a vast interconnected web of filaments, clusters, and voids stretching across billions of light years. Understanding how this grand cosmic architecture forms and evolves is a central quest in modern astrophysics, and galactic cannibalism plays a pivotal role in this story. Through countless mergers and interactions, galaxies not only grow and transform individually, but collectively shape the structure of galaxy clusters and the cosmic web itself. Galaxy clusters are among the universe's most massive gravitationally bound systems, containing hundreds to thousands of galaxies, vast reservoirs of hot intracluster gas, and dominant dark matter halos. These clusters act as cosmic cities where galactic cannibalism is especially prevalent. In such crowded environments, galaxies interact frequently, with larger cluster central galaxies gradually devouring their smaller neighbors through minor and major mergers. This cannibalistic growth of central galaxies, often called brightest cluster galaxies or CD galaxies, leads to enormous stellar halos enveloping these giants. The repeated accretion and assimilation of satellites not only increase the galaxy's mass, but also redistribute stars and gas, influencing the cluster's luminosity distribution and intracluster light, the faint glow permeating the space between galaxies. Moreover, galactic cannibalism influences the dynamical evolution of clusters. As galaxies merge or are tidally disrupted, they deposit stars, gas, and dark matter into the cluster environment, enriching the intracluster medium with heavy elements and sculpting the cluster's gravitational landscape. These processes affect cooling flows, cluster mergers, and the evolution of the galaxy population within the cluster. Beyond clusters, galactic cannibalism contributes to the formation and evolution of the cosmic web, the large-scale filamentary pattern of matter shaped primarily by dark matter gravity. Galaxies form and grow along these filaments, feeding gas and satellites that pile up into groups and clusters. Cannibalism within these hierarchical structures cascades across scales, connecting the histories of individual galaxies with the grand cosmic framework. Simulations incorporating dark matter, galaxy formation physics, and hydrodynamics reveal that repeated mergers and cannibalism feed the growth of massive halos at the nodes of the cosmic web. This hierarchical assembly leads to the present-day distribution of galaxies, from isolated systems in voids to clusters in dense nodes. The imprint of galactic cannibalism is thus visible not only in galaxy morphology and star populations, but in the geometry and evolution of cosmic structure itself. It bridges the gap between the small-scale processes governing stars and gas and the large-scale patterns of matter distribution. Observational surveys mapping galaxy clusters and large-scale structure continue to uncover the fingerprints of these processes, such as stellar streams within clusters, diffuse intracluster light indicating past cannibalism, and correlations between galaxy merger rates and environment. Understanding the implications of galactic cannibalism for cosmic structure enriches our comprehension of the universe's growth, providing a unified picture of how galaxies and the cosmic web co-evolve through time. As we approach the final chapters of our exploration, we will address unanswered questions and ongoing discoveries, highlighting the mysteries that continue to inspire astronomers in deciphering the grand cosmic feast unfolding around us. Despite remarkable progress in our understanding of galactic cannibalism, the cosmos still holds many tantalizing mysteries waiting to be unraveled. As astronomers peer deeper into space and deploy ever more sophisticated instruments and computational tools, new questions arise, challenging our comprehension of how galaxies grow, evolve, and interact over cosmic time. This section invites contemplation of some of the foremost unanswered questions and ongoing discoveries at the frontier of galactic cannibalism research. One fundamental enigma concerns the precise role of dark matter in shaping and governing mergers. While dark matter's gravitational influence is undeniable, the detailed structure and behavior of dark matter halos during complex interactions remain poorly constrained. How exactly do dark matter substructures survive or dissolve during mergers? How do dark matter properties at small scales affect the rate and nature of galactic cannibalism? Addressing these challenges is crucial to refining cosmological models. The physics governing the interplay between stellar feedback, black hole activity, and gas dynamics during mergers also pose significant uncertainties. Starburst-driven winds and active galactic nuclei can both trigger and suppress star formation, but the circumstances that favor different outcomes are not fully understood. Disentangling these feedback mechanisms requires higher resolution observations and more powerful simulations incorporating detailed physics. Another compelling puzzle relates to the frequency and impact of minor versus major mergers across cosmic epochs. While major mergers dramatically reshape galaxies, minor mergers are more subtle yet frequent influences. How cumulative are their effects? Do low-mass satellite accretions significantly alter galactic structure and star formation, or are they mostly peripheral? Furthermore, are there hidden populations of ultra-faint dwarf galaxies contributing to cannibalism in ways we have yet to detect? The fate of central supermassive black holes during mergers also remains an active field of inquiry. Although gravitational wave astronomy has recently begun detecting merging black holes, the coalescence of supermassive black holes in galaxy centers is still cloaked in mystery. What are the timescales and mechanisms governing black hole pairing and merging? How do these processes influence feedback and galactic evolution? Observationally, pushing the limits of current telescope sensitivity and resolution is essential for identifying faint stellar streams, subtle tidal features, and otherwise elusive merger signatures, especially beyond the local group. Upcoming facilities like the Vera C. Rubin Observatory and the James Webb Space Telescope promise breakthroughs, yet mysteries about early universe galactic cannibalism and the smallest scale interactions persist. On the theoretical front, integrating multi-physics approaches, combining gravity, hydrodynamics, radiative transfer, magnetic fields, and cosmic rays into fully cosmological simulations challenges computational capabilities, yet holds the promise of transformative insights. Collectively, these unanswered questions underscore the dynamic and evolving nature of galactic cannibalism research. Each discovery yields fresh complexities, inviting renewed investigation and inspiring innovative techniques. As we approach the conclusion of our cosmic exploration, we will reflect on the human dimension of studying galactic cannibalism. How this pursuit illuminates our place in the universe, connecting the grand cosmic narrative to our own existence and the persistent human quest for knowledge. Throughout history, humanity has gazed at the night sky with wonder and curiosity, striving to comprehend our place within the vast cosmos. The study of galactic cannibalism, these enormous, slow-motion cosmic feasts where galaxies consume one another, connects us intimately to the universe's grand narrative. Far from being mere abstract phenomena in distant realms, the processes of galactic interaction, growth, and transformation resonate deeply with us, illuminating not only cosmic history, but our very existence. By unraveling how galaxies evolve through cannibalism, astronomers reveal the dynamic universe as a place of continuous change and renewal. This perspective helps us grasp that the Milky Way itself, our stellar home, has been shaped through countless mergers and accretion events, absorbing smaller galaxies over billions of years. Understanding this cosmic ancestry situates humanity within a long chain of cosmic evolution, linking our origins to these grand universal processes. Furthermore, studying galactic cannibalism enhances our awareness of cosmic interconnectedness. Galaxies do not evolve in isolation, but are part of vast structures where matter flows through the cosmic web, where dark matter halos govern interactions, and where gravity orchestrates dances spanning eons. Recognizing our galaxy's participation in this cosmic society enriches our appreciation of nature's complexities and continuous transformation. Engaging with the science of galactic cannibalism also exemplifies humanity's capacity for exploration, creativity, and discovery. Through advanced technology, powerful telescopes, sensitive detectors, and supercomputer simulations, scientists piece together faint signals across immense distances and timescales. This collective endeavor reflects our enduring drive to comprehend the universe and our place within it. Moreover, the revelation of galactic cannibalism challenges and expands humanity's philosophical outlook. It invites us to consider the universe as a dynamic, ever-changing arena where creation and destruction coexist in delicate balance, where galaxies live, die, and are reborn through cosmic interactions. This viewpoint fosters humility and awe, inspiring questions about life, time, and existence on scales far beyond our daily experience. Finally, studying these grand cosmic phenomena inspires educational and cultural reflections, encouraging scientific literacy and curiosity. It reminds us that the atoms making up our bodies were once forged in stellar furnaces, stars born within galaxies forged through mergers and growth, binding the story of human life seamlessly to the cosmos. In this way, the investigation of galactic cannibalism serves as a bridge connecting cosmic science with human identity. It underscores how our quest to understand galaxies mirrors a deeper search to know ourselves and the universe we inhabit, binding the celestial with the personal, the universal with the intimate. As we conclude this cosmic journey, we celebrate not only the remarkable science of galactic cannibalism, but also the human spirit that drives us to explore the stars and seek meaning in the vast expanse of space and time.